All right. Anybody have any homework questions? 25. Okay. All right. So there's an incline at 20 degrees, and there's a block on the incline with a mass little m, and there's a pulley and a cable connecting that mass little m to another mass of little m that's hanging over the side. It's the smallest coefficient of static friction. Uh, the smallest, that wording is a little messed up, but so what's the smallest coefficient of friction where they would stay at rest? So what's the smallest mu sub s? So the blocks would stay at rest. Basically, we're looking for the coefficient of static friction that's exactly at the border between starting to move and staying still. Well, when we analyze this block, because we're going to have to do free body diagrams of both of these two objects, we're going to use the coordinate system that we use for sliding and rolling. And when we isolate the hanging one, it's not sliding or rolling, so we're just going to use the regular coordinate system. I'll call this one block 1 and this one block 2. So free body diagram of 1. We have a downward force of mg, a normal force perpendicular to the surface, a cable force T, and then we also have a friction force. If you can't tell from looking at that picture what would happen if there was no friction, then you kind of have to do this problem without friction and see which way the system is going to accelerate. And that would be a huge pain. So I'm going to, well, notice there's two forces that are fighting each other, okay? So if there was no friction force, the weight force of this would be trying to pull it down that way. And the weight of this one would be trying to make it accelerate the other way. So you have to figure out which way it's going to accelerate, you have to know which one of those is going to apply a bigger force. The answer is if there was no friction, it would go that way. But when you have things going in two different directions like that, it's not always super clear. To be totally like if you had all the time you wanted, but you had to get this problem right, if you didn't have any mathematical reasoning about it, you would just have to do this problem without friction, calculate which direction the acceleration is, and then go back using that direction to determine the friction direction. Any questions about what the hell I'm talking about? Okay, so, but what we would get if we did that problem without friction is that the system would accelerate, mass 1 would go up and to the right, mass 2 would go down. So the friction force is opposite of that. And For static friction, I'm going to sort of do this the way I always do it for static friction. I'm just going to calculate this force F that's required for it to be at rest. And then I'm going to go back and figure out what the maximum value of that force of friction is and do the comparison after. Our coordinate system is like this. Our weight force is this. The angle between the negative y-axis and the weight force is always the same as the angle between the horizontal and the incline. So this angle is 20 degrees. And so if we're trying to find this angle theta, that's going to be 20 degrees short of 270, so 250. And so that weight is going to be mg times cosine and sine of 250. And that is negative 0.342 mg, negative 0.940 mg. And now Newton's second law. We have the negative friction force in the x direction, weight force, the normal force, the cable force, and that's all equal to the mass times the acceleration. What acceleration do we want to use here? Yes, exactly. This is static friction, so we're going to assume that it's at rest. And so mass times 0 is just equal to 0. For these friction problems, we almost always need to know the normal force. So I'll use the y equation to tell us that N is equal to positive 0.940 mg. And then the x equation says the force of friction is equal to T minus 0.342 mg. And now I'm going to set these two equations aside and isolate the other one. So a free body diagram of the hanging mass has the weight mg down and the cable force T up. And this one we're using a normal coordinate system, so this one's pretty easy to come up with the components. This is just 0, negative mg, plus 0t is equal to, what's the acceleration of this one? Zeros, yep. If the other one isn't accelerating, this one isn't accelerating. So the y equation here gives us T is equal to mg. So now we can plug, we have a system of 3 equations for 1, 2, 3 variables. I'll plug mg in for t in the x equation above, and we get this new system of 2 equations that say N is equal to 0.940 mg. And the second one says the force of friction is equal to mg minus 0.342 mg. So that's 0.658 mg, right? Now we're looking for the coefficient of friction. We're looking for the mu sub s, where the block is just about to slide. So our force of friction is 0.658 mg, and that's equal to mu sub s times the normal force. We know those are equal if it's right about to slide. Generally, we know that the force of friction is less than or equal to this. But if we're right at that boundary, then it's equal. And so 0.658 mg is equal to mu sub s times, I'll plug in what we know about the normal force. And you can cancel out the mg's. And so mu sub s is equal to 0.658 over 0.940. And what do you get for that? 0.70. And what are the units on coefficient of friction? Nothing. Yep, exactly. Any questions about that? Any other homework questions? Sure. Okay, so this is just asking for a net force vector. This is a funny one. It's sort of going back to, could have done this one a long time ago, it looks like. A 15 kilogram mass is moving in a circular path. Circle. The radius of this circle, the length of the arm is 0.5 meters. The instant shown, the arm has a clockwise angular velocity of 12 radians per second and a counterclockwise angular acceleration of 10 radians per second squared. And we just want the net force. This object has a mass of 15 kilograms. Since the angular velocity is clockwise, the velocity vector is down. Since the angular velocity and angular acceleration have opposite directions, the tangential acceleration is this way. Centripetal is always this way. magnitude of the centripetal acceleration is omega squared r. So that's 12 squared times 0.5, which is 72. That's in the negative x direction if our coordinate system is this. So the total centripetal acceleration, the centripetal acceleration vector is negative 72, 0. The magnitude of the tangential acceleration is times r, absolute value. Yep, so that's 10 times 0.5. So that's 5. Okay, hold on a second. This is an enforced break. Okay, so I got to rewrite some of this stuff. Centripetal acceleration is negative 72, 0. Magnitude of the tangential is 10 times 0.5, so 5 meters per second squared. That's in the positive y direction, so the tangential acceleration vector is 0, 5. So the total acceleration vector is negative 72, positive 5. Based on what we drew here, is that in the right quadrant? Yeah, we could tell that it has to be in the second quadrant here, so it has to have negative x component, positive y component. That's what we got. And now, normally, to use Newton's second law, we draw a free body diagram, but this is just asking us to calculate the net force, not individual forces. And so Newton's second law says the net force is just equal to the acceleration times the mass. So that's a mass of 15 times the acceleration of negative 72, 5. And that is negative 1080, positive 75 newtons. Any questions about that? Any other homework questions? Okay. So I want to just say something really quick about, so my last comment on particle kinetics. Newton's second law is the equation, the only equation that we have that relates force and mass to kinematics. It relates it to acceleration. In order for Newton's second law to apply, in order for it to hold, the kinematics must be calculated in an inertial coordinate system. And there are two requirements for a coordinate system to be inertial. The first one is that the origin of the coordinate system can't be accelerating. So, for example, if your kinematics are calculated from a video camera, this is a little wordy, but if your kinematics are calculated from a video camera that's mounted to an accelerating vehicle, then those can't be used in Newton's second law. We've done an example where we saw that with a camera that was mounted to an elevator that had a downward acceleration. We did a few of these elevator type problems. But if you think of the elevator being in free fall, it makes sense that how this works. If elevator's in free fall and you drop an object, which you certainly would do if your elevator started to be in free fall, that would be surprising, not in a good way. And so the elevator's accelerating downward at 9.81. You let go of an object. It's also in free fall, so it's accelerating down at 9.81 meters per second squared. But to you, it would look like this object is just hovering there next to you, okay? And that object does have a force on it. So if you, in the small amount of time you had left on Earth, decided to try to calculate, use Newton's second law, see if Newton's second law held, you'd see that this thing had a zero acceleration because it looks like it's just hovering in space. But you know that gravity's pulling down on it, and so you'd get something equal to zero. It doesn't hold. Okay. And the second requirement is that the coordinate system can't be rotating. And again, you can think of if you're recording your kinematics are calculated from a video camera around in a circle. Um, then those kinematics can't be used with Newton's second law. Um, and to picture that, I think the easiest way to picture it is imagine an astronaut in one of those training things that I've drawn once or twice, going around in a big circle. That thing's designed to accelerate the passenger, create a lot of acceleration. Now imagine that the video camera, so the passenger is out there at the end of an arm, and imagine that the video camera is just sitting in place, just following the passenger as he goes in this big circle, okay? Um, well, then to that video camera again, uh, the camera just sees a person sitting there screaming for no reason, like the blood draining from their face for no reason. And so if you calculated the kinematics in that coordinate system from that video camera, you would see a person with a constant position. So the velocity would be zero the whole time, the acceleration would be zero. But if you measured the forces in the chair, there would be big forces required because the person's accelerating a lot. And again, it would look like Newton's second law didn't hold. Okay, so you have to be sure that when you use these, when you use Newton's second law, you have to be sure that your coordinate system is inertial. Yes. Mhm. Yes. Yeah. So to picture what that measurement would do mathematically, so um, you have to just picture that all the camera's doing is looking at the one object that they're tracking and using whatever tools it has to measure where that is compared to the camera. That's the idea. And so, yes, you could use the surroundings to figure some things out, but um, imagine that all this camera only has one job to figure out the change in the location between the camera and the whatever object or passenger or whatever. What about cameras fixed on the surface of the Earth? Because it would be a major pain if we couldn't use measurements on the surface of the Earth. Well, they're accelerating and rotating. Um, it's usually okay though. Well, usually. Because the acceleration is small and the rotation is slow. Um, so these only cause problems for very precise experiments. Okay, so in other words, Newton's second law only works for inertial coordinate systems. The Earth, surface of the Earth, you can't have an inertial coordinate system fixed on the surface of the Earth. So really, technically, actually, you cannot, Newton's second law does not apply for any measurements you take on the surface of the Earth, but it is very close to being accurate. Close enough to being accurate that any measurements you'll do in your time in school, it'll work fine. You know, there are some cases where people do experiments that are sensitive enough that they have to take that into account, though. Any questions about that? Okay. So now we're on to the next topic. Linear momentum. And linear momentum is going to, okay, this is going to be a pain, so get ready. We're going to denote linear momentum as a lowercase p vector. Okay, we've already used a lowercase p vector, and so you're going to have to differentiate whether you're talking about momentum or position just based on the context of the problem. Okay, I wish we had more letters in the alphabet, but we don't. Uh-huh. Yeah, that's true. That's a good idea. That might revolutionize physics. Um, so the linear momentum is the mass of an object times its velocity vector. And so it's a vector. So it has a magnitude and a direction. Uh, and the direction is the direction of the velocity vector. So the direction is where the object is moving, the direction the object's moving. The magnitude of the momentum and I'm going to just call it momentum a lot, but there is actually an angular momentum too. This is just a linear momentum. But the magnitude of momentum is, roughly speaking, how much it would hurt if the thing ran into you. Okay, so compare, for example, the magnitude of uh, let's say the mass is 0.05. That's my guess at the mass of a tennis ball. That would be in kilograms. And a speed of 40 meters per second. Okay, that's pretty fast, almost 100 miles an hour. But it's a tennis ball, so you'd feel it hit, but you'd be fine, you know. So what's that equal to? That's 2 kilogram meters per second. Okay. Doesn't hurt too much. Yeah. And now let's think about the magnitude of the momentum for a Ferrari. What's the mass of a Ferrari? 1,000 kilograms? Okay. I don't know. Let's imagine it's whatever kind of car weighs 1,500 kilograms. Actually, I'm going to make it 1,000 because it's so much easier for me to calculate. And let's say that's going 40 meters per second. Okay. So it's going the same speed, but that mass makes a big difference. And now you have 4,000 kilogram meters per second, and it only hurts for a second. Oh, yeah. Thank you. That's the new math. Only hurts for a second. Okay. So, what football coaches are mostly looking for is they're looking for a bunch of people who, they're trying to maximize the ability to produce linear momentum. They're looking for, like, they like fast people, they like giant people, but what they really, really like are really fast, really giant people. That's where you maximize the momentum. Um, we'll use linear momentum in two results. And both involve, both are useful for impacts, collisions, and explosions. These are the only really useful applications for momentum calculations. The first one is the impulse momentum equation. And it says that the change in an object's momentum is equal to the integral from time 1 to time 2 of the net force with respect to time. And I'll derive that, show you where that comes from. But that first one is a relationship between the change in momentum and forces applied. And the second one is conservation of linear momentum. And that says if the net force on an object is 0, and when I say object, it could also be a collection of objects or a piece of an object, whatever you're isolating. If the net force on what you're isolating is 0, then the object's linear momentum at instant 1 is the same as the object's linear momentum at instant 2. Okay, so conservation means stays the same. So if there's no net force acting on the object, the linear momentum of the object stays the same. So first I'll talk about the impulse momentum equation. And notice that in terms of momentum, in terms of P, we can rewrite Newton's second law as the net force is equal to the time derivative of the linear momentum. Time derivative. Okay, because the linear momentum is the mass times velocity. The time derivative of the mass doesn't change. You know, the time derivative of the mass is 0. And so the time derivative of the linear momentum is just mass times acceleration. And that's what we had before, right? This, you can think of this as the time derivative of mass times velocity, and that's just equal to mass times acceleration. And in fact, in Newton's original, his original writing about this gave Newton's second law in terms of momentum. It was later that people started finding it to be efficient, I guess, to think of it in terms of mass and acceleration. But so if you integrate both sides of Newton's second law, with respect to time, you get the integral of F net, let's see, over whatever time interval you're dealing with, we'll call that time 1 to time 2, is equal to the integral from time 1 to time 2 of, right, this is dp dt with respect to time. And then you can rewrite that as the integral from t1 to t2 of f net dt is equal to the change in the momentum over that time interval, or you can also think of that as the momentum at time 2 minus the momentum at time 1. And this is useful for calculating average contact forces over small time intervals. Okay, so let's, how long is this going to take? Okay, so let's say that we want to calculate the what's the average contact force that a baseball bat applies to a ball um, during a 0.01 second contact. And over this contact, the ball's velocity vector goes from let's see, 40 meters per second this way. So toward the bat, and this angle is 5 degrees. I guess I'll have to, am I going to finish this? To 50 meters per second this way, where this angle is 30 degrees. And the mass of the ball is right about 0.1. A baseball is 0.145 kilograms. Let's just call it 0.1 kilograms. Okay, well, notice that over these short duration impacts, you can imagine this average force is going to be pretty big. And in cases like this, a lot of times we'll just leave the weight out of the problem. So the net force is the contact force applied to the ball plus the weight of the ball. Let's just assume that F net is much bigger than the force of the weight on the ball. And so we're going to assume that that net force is really pretty much just the contact force. That's a pretty common assumption. So what we have to do is first calculate the momentum of the ball at instant 1 and instant 2. And then use the fact that the average force relates to the integral of the force, I. So F average times the elapsed time is equal to the integral from T1 to T2 of F dt. Okay. Let's just finish that next time. But that's pretty much the set of steps for any problem you do. Some problems, it might say that you can neglect the weight force. Some problems, the weight force might be more important, so you have to subtract that out at the end, but this is the basic idea.